So let's say that we wanted to go through and identify the degree of each of these functions. Now, for example, these are all polynomials, but some of these are written in factored form, and this one here is in standard form. When a polynomial is in standard form, you essentially look at all the terms and you look for the largest exponent. Here, the largest exponent is 4. So we'd say that, for example, A, the degree of this polynomial is 4. But for something like this, for part B, where it's not in standard form, what you could do, if you wanted to, is you could expand it. For example, x minus 7 squared is the same as x minus 7 times x minus 7, which, if you bust out your algebra 1, would give you this. Then you can clearly see that the largest degree, or the largest exponent, is 2. And so the degree for that function would be 2. However, for something like this, are you and I going to spend half an hour expanding this 13 times? Of course not. We don't have time for that. But what I want to throw at you is this. Now, over here, let's use the easy ones as an example. Notice that the largest piece is the one that has the largest exponent, right? That's the most important part. All of these pieces are irrelevant. These are irrelevant. The only thing that matters is the largest exponent that is created. Here, can we agree for this problem that if you were to take x plus 4, and do it 13 times, that if you did all of this business over and over and over, that at the end of the day, you'd get x to the 13th plus a bunch of smaller, irrelevant pieces, if you will. That's what would happen. You'd have something that's x to the power of 13. Which is why, for example, C, the degree would be 13 because that's the largest exponent that would be created. Are there a bunch of other smaller, inferior pieces? Yup. Do we care about these smaller pieces? Nope. All we care about is the largest exponent that would be created. How about here? This has a lot of pieces glued together. So let's take this one bit at a time. For example, that's just the coefficient. Ignore it. Looking at this piece here, this is just x squared. That's the strongest piece in this little chunk. How about right here? If you went x plus 5 and raised it to the power of 4, can we agree that this piece would give you a lot of pieces, but that the strongest piece of them all would be something that's at x to the 4th? Similarly, here, if you expand this 7 times, it's going to take a whole paper, but the strongest piece would be something that says x to the power of 7. So if you add these exponents together, it gives you, again, something that says x to the power of 13. There will probably be some number there and a bunch of other pieces here. How did I get 13? I said 2 plus 4 plus 7, which is 13. So for this one, the degree is 13. One more here. How about this? Here, there's just negative there. So here, look, if you took all this to the power of 10, the strongest piece that would be created is x to the power of 20, because you essentially go 2 times 10. X to the 20th would be the strongest piece. All of these pieces are inferior to this. How about here? This strongest piece would be something x to the 15, because it's 5 times 3. A bunch of other pieces would be created. We don't care about those. So essentially, for this one here, the degree would be 35, because you go 20 plus 15. One more. I think I have it. Actually, no, that was it for that. Another idea, though. Another idea that is very relevant and very connected is this idea right here. And that is, here's a fact. The graph of a polynomial of degree n can have at most n minus 1 turns. Let me just write this word again. Turns. So what do we mean by turns? For example, just go pencils down real fast. You know that the graph of x squared looks something like this. And here, that is what we call a turn, because the graph turns from going down to up. Notice there that for this random problem, the degree was 2 and the number of turns was 1. Check this out. How about x cubed plus some other gibberish? The graph of x cubed can potentially look something like this. This has a turn here, and it has a turn there. So here, the degree was 3, and the number of turns was 2. How about one more before we do some exercises? How about like x to the 4th plus 3x cubed plus some other gibberish? X to the power of 4 can probably look something like this, where for this function, the degree would be 4. And how many turns does this graph have? Turn, turn, turn. It has 3 turns. You're starting to see a relationship. Whatever the degree is, if you subtract 1, boom, boom, boom. If you take away 1, that tells you how many turns the graph could have. So, for example, back to this random problem here. The graph of a polynomial of degree n can have at most n minus 1 turns. So, state the number of turns that each of these functions could have. Okay, for example, A. Here is a polynomial of degree 13. So, how many turns could we have? At most, 12 turns. How about part B? Well, first of all, for part B, can you tell me what the degree is? Using the concepts we discussed earlier. The degree would be 28, right? 28. So what does that tell you about the number of turns that the graph could have? It could have at most 27 turns. It doesn't have to use all 27, but it could. How about for this one here? First, let's identify the degree. So we look at all of the pieces, and the shortcut is you multiply the strongest exponent with the outer exponent. So here that's just x to the 4th. Here the strongest piece would be something x to the 24th because 8 times 3 is 24. Here, make that look nicer, 9 times 6 is 54. And so these are all the pieces that would be created. And so the degree of this would be, what happens if you add all these? That's 78 plus 4 is 82, which means that the number of turns would be at most 81. This graph could have 81 twists and turns. Probably something crazy like this where you have 81 turns. Why do I keep saying at most? Because you don't have to have all the turns. For example, x to the power of 4 has degree 4, but the actual graph of x to the 4th looks like this, where it only has, this one only has, it has only 1 turn. But the point is, if I add some more pieces to it, the graph could look something more like this, where you have a maximum of up to 3 turns. So whatever the degree is, you subtract 1, and that's how many turns the graph could have.